Hello again, everyone. Welcome to this video of our discussion of section 1.2, where we will talk about functions and their graphs. So before we start, I want to remind you about how to study for this class. Spend 30 minutes to 45 minutes to skim through the textbook section before you watch this video or attend class. After that, attend class or watch this video and take notes of the things that you might have questions on and the things that you think are particularly important in the discussions that you see. Third, review these lecture notes or the textbook section and solve all the problems you see, either in the book, the solved problems that they have in the book, or the problems that I solve here in the class. Solve all these problems again on your own without looking at the solutions. Resist any temptation to look at the solution in the book or watch my solutions here without having given yourself the opportunity to solve these problems first. A critical part of learning this subject is that you must, and nobody can do this but you must give yourself the opportunity to solve these problems before you see somebody else's solutions. Okay? And then complete all the homework assignments by the due date. This helps you catch questions early because we intentionally pick these problems to catch any questions you might have, and you would come, the expectation is that you bring up those questions to us, the faculty, so we can answer them for you as the semester progresses. So it's critical that you complete all the homework assignments by the due date. And of course, throughout this semester, review all the previous material, because mathematics by nature is a cumulative subject. So anything we learn now depends on the stuff we learned before, and anything we learn in the future will rely on the stuff we're learning now. Okay? Because of the cumulative nature of this subject, please make sure that you spend half an hour a week. It doesn't have to be every day. Half an hour a week. Take a look back at the stuff that we've talked about during that week or the weeks before. I say half an hour because when you stay on track of reviewing the material consistently and regularly, you won't need much time to review. Just a glance at material from the past will help you remember everything you learned. That's the nature of review. But if you don't review, and 3 months down the road, when you prepare for the cumulative final exam, it's going to be very difficult to catch up and remember everything you've learned or everything we've talked about in the class. So please review consistently and regularly, and that way, remembering the stuff in the future, especially for the final exam, will be very comfortable and easy. Okay, so now to our discussion of section 1.2. The anatomy of an equation should be very well known to us, which is basically the x variable. Usually we call it x, right? But it could be called anything. It could be called n, it could be called k, h, p, anything. But this variable that is part of the main function is called the independent variable. And all the values it can accept, they are called domains. So the domain of any function is all the values of x, or all the values that are acceptable as the independent variable value. All those values are called the domain. Range is y is the dependent variable, and all values that it can take is part of what we call the range of a function. Okay? So please make sure that you carefully read this diagram and understand what it's saying. So some people also look at X and Y as input-output. That's how they define it, as a machine that accepts an input and produces an output after accepting an input value. Some people like to think of it like that. So not every equation is a function. And a function is an equation. This is a concise definition of a description of it. You can find this in the book as well. So I thought I included here. A function, so, is an equation such that for each member of the domain, so each member of the domain, that means each x value, for each x value, there must correspond one member of the range, or the y value. Okay? So for each domain, we must have exactly one. I might as well insert here, exactly one member of the range. So in this exercise, it says determine whether the relation is a function or not. If it is a function, identify the domain and range. So here we have the member of domain, right? So this is part of the domain. 3 is part of the domain. 1 is part of the range. 5 is part of the domain. 1 is part of the range. 7 is part of the domain. 1 is part of the range. Right? So for each member, if we look back at this description, for each member of the domain, 3, 5, 7, there must correspond one member of the range. 1, 1, 1. So is this a function? This is a function. It agrees, or it satisfies that condition, that description, not condition, but description for a equation to be for a relationship between x and y to be considered a function. So this is a function. So again, for each domain value, we have exactly one range value. Okay, this is a function. So that's clear. Now it says identify the domain and range. Because here we have 3 points, so the domain is going to look like this. So domain equals 3, 5, and 7. That's it. And the range is equal to one value, 1. Okay? So this is a function, yes. Here's the domain, here's the range. How about the one underneath it? This one. Well, that 1 is domain. The 3 is the range, right? The 1 is domain. The 5 is range. The 1 is domain. 7 is the range. 1 is the domain. 9 is the range, right? So, for 1, 1, 1, 1, which is the part of the domain, how many values of the range we have? As far as we know, it's at least 4, right? So with one value of the domain, the case we have is that for one value for each member of the domain, which is 1 in this case, there must correspond exactly one member of the range. Do we have that? No. We have for one value of the domain, we have 4 values associated with it. So this is not a function. This is not a function. Okay? So we don't have to give the domain and range. It is not a function. Let me actually describe more. So this is not a function because there are 4 values of the range associated with 1 value in the domain. Okay, that's why. Here it says, given this function, or given this expression, function, find these values. Okay, please pause the video, answer this question, then come back to the video. Okay, I'm assuming you've done that. So the function at 0 is 5 times 0 squared plus 4 times 0, right? We substitute for x with 0, and we get 0 plus 0, which is 0. Okay, so that's the answer for that. The function at 3, we substitute for x with 3. So 5 times 3 squared plus 4 times 3. 3 squared is 9. So 5 times 9 plus 4 times 3 is 12. 5 times 9 is 45. Plus 12, it is 57. T minus 1. So the function argument, the argument of a function is, in this case, is x. So that's called the argument of a function. The argument of a function not only accepts numbers, that's not the only thing it accepts. It accepts other variables as well as numbers, just like this case, t minus 1. So wherever you see x, we need to replace with t minus 1. So I hope you're paying close attention to this. So look at this as I'm writing. So 5. Instead of x squared, replace x with t minus 1 and then square. Do you see what's happening? The x is gone, t minus 1 squared instead of x squared. How about that? The next one, or the next term, plus 4 times, instead of x, 4 times t minus 1. Okay? Now, we have to expand this or simplify this, because right now we have things we need to combine. We need to expand this and expand this such that we can combine the constants, we can combine the t terms, we can combine the t squared terms, and so on. So, to expand this one, you have 2 choices. Either you FOIL it, in other words, either you do this, either you'll do this, so t minus 1 squared is equal to t minus 1 times t minus 1. And then you FOIL it. You can do that, right? That'll take some time. Or you remember the special product formula. The special product formula, and I'm going to use a scratch paper to remind you of that. These are the things you should, not only you should remember them, but they are worth memorizing. They facilitate your problem solving a great deal. So suppose you have a, instead of a, we had a formula, a minus b squared. This, we have a special product formula here that we say that if you have that, then the first term squared, that's minus, so minus twice the first term times the second term, so minus 2 times ab, plus the second term squared. That's a formula. If you remember this shortcut formula, you can quickly write down what t minus 1 squared is. If you FOIL it, like I was saying earlier, you can get the same answer, but it'll take you a while. So let's see how. So if you remember it, quickly you can write it down, right? But what if you don't remember this? If you FOIL it, you'll have to do a minus b times a minus b, right? For a minus b squared. Then you have to FOIL it. You say a times minus b. So what do we get? a times a is a squared. A times minus b is minus ab. Then distribute minus b into the a minus b into minus b. So what do we get? Minus b times a minus ab again. Minus b times minus b is plus b squared. Equals a squared, add these two, minus 2ab plus b squared. Compare this with that. So you get the same thing. But look how much more time foiling takes than memorizing this and writing it down immediately. The same way works with t minus 1 squared. If you remember the special product, then you're going to do this. You're going to say, oh, t minus 1, given this formula, which applies to any such thing, any entity minus another entity squared uses the same formula. You say t squared minus 2t plus 1. I'm done. That's if you remember this, right? The first term squared, t squared, minus twice the first term times the second term, minus twice t times 1, minus 2t, which is that, plus the second term squared, plus 1 squared. There you have it. So you have t squared minus 2t plus 1. So you choose what you want to do. Do you want to keep foiling, which is fine, but it'll take more time, especially, which is critical, especially during exams. Or you can just remember this formula and you remember how to apply it, and you quickly write down the answer for things like that. Okay, the choice is yours, but I highly encourage you to memorize the special product formulas. There's a whole bunch of them. Okay, that you should. I mean, the whole bunch, I mean, there's at least 3 of them that are very, very important in this class. And then there are a couple of them that are less frequently encountered in our solutions. But they're useful nonetheless. But they're the cubic functions. Okay? But those 3, those 3 that I'm mentioning are very critical. I might as well tell you what they are. Those 3 that I'm mentioning, special product formulas that are very critical, are these. So a plus b squared is equal to a squared plus 2ab plus b squared. Now the same thing has a minus in between, right? Which is the one we just did for our example. A squared minus 2 times the first term times the second term plus b squared. So that's the second. The other one is if you have if you have x squared minus y squared, that's equal to x plus y times x minus y. Or if you have x plus y times x minus y, that's the same thing, written differently. If you have that, it translates into this. This is equal to x squared minus y squared. So all these equations go both ways. So if you have that, you can write it in factored form like this. If you have that, you can write it in factored form like that. If you have this, you can write it in factored form like that. So these are the 3 special product formulas that are hugely useful. These 3. These 3. Okay? And the other 2 are much less frequently encountered. So we'll talk about those when we get to them. But these 3, make sure that you remember them. It just takes a little bit of practice. Everything you learn in this course is highly procedural. Anything procedural, it takes a little bit of practice to become excellent at it. But with a little bit of practice, you can get there. And of course, the study tips that I give at the beginning of each video. Remember that? I'd like to keep repeating that for a number of videos just to make sure that you remember them constantly. Okay? Those are very, very important when you study mathematics and any quantitative subject. Okay, so expanding this, we get 5 times t squared minus 2t plus 1. And let's distribute this 4 into this. We get 4t, 4 times minus 1, minus 4. Right? Are we done? No, we need to distribute the 5 into this. So we have 5t squared minus 10t, 5 times 1, 5. Right? 5 times t squared, 5t squared. 5 times minus 2t, minus 10t. 5 times 1, plus 5. Plus 4t minus 4. Now let's combine the things we can. So we have 5t squared minus 10t plus 4t minus 6t. 5 minus 4, positive 1. So there. So the function, the original function at t minus 1 equals that. Okay. All right, so we're going to replace x with negative 1. Okay, so let's do that. So let me put the original function here, because as I move the paper up, it's going to go off the screen. So the original function was f of x equals 5x squared plus 4x, right? We're evaluating this function at these different values. And I'm hoping that you already have your solutions done. Okay, so f at negative 1 equals 5 times minus 1 squared plus 4 times negative 1. So that is equal to 5 times minus 1 squared is positive 1. 4 times negative 1 is minus 4. So 5 times 1 is just 5. Minus 4 is 1. Okay. Now let's replace in this equation with t. So wherever you see x, you need to replace it with t. So we have f at t is equal to 5t squared plus 4t. Right? There we have it. So notice when you have a number in the argument for x, you end up with a number. When you have a variable, you end up with a whole different, with this function. Okay? All right, so we continue our examples with this one. It says given this function, so the function changed, right? But the procedure is the same. Evaluating a function at different values, it stays the same, right? So let's do that. So replace wherever you see x with 1. So we have 2 times absolute value of 1 plus 3 times 1. Absolute value of 1 is just 1 times 2, it's just 2. Plus 3 is equal to 5. So we evaluate the function at a number, we get a number. Not here though. We're evaluating a function at a new variable form. So we're going to get a new function. So equals 2 absolute value of minus x plus 3 times minus 1. Minus x. Sorry about that. So instead of 3x plus 3 times minus x. So let's simplify. We get 2 times absolute value of negative x and plus 3 times minus x minus 3x. There we have that. Okay. Substitute for 2 minus h in there. So 2 times absolute value instead of x, 2 minus h. Are you following what's going on? I hope you are. 3 times instead of x, 2 minus h. 2 minus h replaces wherever you see x. Okay? So, continuing here, we have 2 times 2 minus h plus let's distribute this. We have 3 times 2 is 6. 3 times minus h, minus 3h. Okay? So we might as well write it in a form where the constant comes last. So this is equal to 2 times 2 minus h minus 3h plus 6. I just rearranged these so the constant comes last, like that. Okay. This function at negative 2. So let's evaluate it. We expect to get a number, right? Because we're evaluating a function at a number. So 2 times absolute value of negative 2 plus 3 times negative 2. What do we get? Absolute value of negative 2 is positive 2 times 2, it is 4, right? And plus 3 times negative 2 is minus 6, so the result is negative 2. That's interesting because we evaluated the function at negative 2 and we got negative 2. That's possible, which this was such a case. So 2y, wherever you see x, you replace it with 2y. So we're evaluating this function at some term that has a variable in it. So we're going to end up with a number? No, we're going to end up with a new function. So let's see. So 2 times absolute value of 2y. Notice wherever I have x, I'm going to replace it with 2y, the new argument. See, the argument of this function was just x. Now we're modifying it based on new arguments, argument values or arguments with different variables. Okay? This happens a lot in mathematics. You have to be very comfortable with it. So plus, instead of 3x, I'm going to say 3 times 2y, right? So that's equal to that. So we have 2 times 2y plus 6y. Like that. Okay? So here we have what is called a rational function. This is called a rational function. Okay? We're asked to evaluate this rational function at these 3 values. I mean, 2 of them are values. The third one is just other variables. That just means wherever you see x, replace it with x plus h. Please don't make this harder and overthink it. It's very easy. Wherever you see x in the original function, replace it with x plus h. Don't think back at, oh, I have an x here, I have an x there. No. Wherever you see x, replace it with x plus h. That's all there is to it. Okay. So please, on a piece of scratch paper, finish this page, which is page 3, on a scratch paper, and then come back to the video to see my solutions. Okay, so I hope you've done that, and now you're back. So evaluate this rational function at 5. So wherever you see x, replace it with 5. 5 minus 4 divided by 5 plus 3. What do we have? 5 minus 4 is 1, positive 1. 5 plus 3 is 8. So that's it, 1 over 8. So that's our answer for that. So now replace x with negative 3. Negative 3 minus 4 divided by negative 3 plus 3. We have to stop here because negative 3 minus 4 or negative 7 divided by 0, that is undefined. Undefined. Does not exist. Okay, the value of this rational function at negative 3 does not exist because we end up dividing by 0 when we plug in negative 3. We were talking about domain earlier, right? So the domain of this rational function must exclude -3. Okay? We have more examples on domain, so I'm going to wait until we get to those. So evaluate the function at x plus h. So wherever you see x, I need to replace it with x plus h. Gx plus h equals, instead of x, x plus h minus 4. Do you see what happened? Compare the numerator here with the numerator here. X is gone. Instead, you have x plus h. In the denominator, the same thing. X plus h plus 3. So what do we get? We get x plus h minus 4 divided by x plus h plus 3. Can we simplify x and x? Absolutely not. These are being added and subtracted from each other. We cannot simplify x by x because x is being added to that and x is being added to this. If x was being multiplied by h minus 4 divided by x multiplied by h plus 3, then we could get rid of the x. We could cancel it in multiplication case, but that's not that. Okay? So there's nothing else we can do to simplify this. This function at different values, 5a, -7, -4. Please pause the video, write down your solution, and then come back to the video again. So we have, I'm assuming you've done that. So whenever I see x, I'm going to replace it with 5a. 5a squared minus 5a plus 3. 2 times 5a squared is 25a squared minus 5a plus 3. Let me simplify it a little more because I need to distribute the 2 out here. 2 times 25 is 50a squared minus 5a plus 3. Like that. Okay, I hope this agrees with what you have. So equals 2 times, wherever you see x, replace with -7. So 2 times -7 squared minus x becomes minus 7 plus 3. Okay, so 2 times -7 squared is 49, positive 49. Minus 7 is positive 7 plus 3 equals. So 2 times 49 is 98 plus 7 plus 3. So 3 plus 7 is 10. 10 plus 98 is 108. Like that. I hope this is making sense. So now the argument changes from x to a minus 4. That means wherever we have x, we need to replace it with a minus 4. So we have that function, right? So 2 times, instead of x squared, we now have a minus 4 squared. Notice I replaced x with a minus 4. And the power then applied to a minus 4 because it was applying to x. Minus x becomes minus a minus 4 because a minus 4 replaces x. And of course, plus 3. Are we done? No, because we need to expand this, right? Expand this using this special product formula, that one. A minus b squared, we're going to apply that again. These 3 formulas that I ask you to remember. Very, very important. So 2 times. If you remember that, it's very easy to expand this. A squared minus 8a plus 16. Minus, then let me distribute the minus into this. Minus a minus a. Minus minus 4, positive 4. Plus, of course, 3. The reason these 3 formulas are very, very commonplace. Their application is very, very common. So if you memorize them, they pay dividend to you again and again and again. Every class, every exam, they pay dividend to you. So they are well worth memorizing. Okay, so let's distribute the 2. We have 2a squared. 2 times minus 8 is minus 16a. 2 times 16 is positive 32. Then minus a, 4 and 3 add up to 7. So let's take this further if we can. Yes, we can. We have 2a squared minus 16a minus a. They add up to minus 17a. Positive 32, positive 7. They add up to positive 39. Okay, like that. In exams, sometimes I see people leave it like that. You lose most of the points if you do that. You need to, or they write this or leave it like that. Okay, you might get 1/3 of the points if you leave it right there. Okay, so you don't want to do that. You want to distribute. You want to simplify you want to simplify the function as much as possible. Okay. So recall from section 1.1. That's the section we did in the last video. That one easy way to graph a function is found by finding its x-intercepts and y-intercepts, right? We learned that. X-intercept is when you have the y component equal to 0 and you're looking for x. Y-intercept is when you have the x component equal to 0 and you're looking for the y value, right? Remember that? And then connecting the points with a smooth line. So graph each function below by using a table of values, which is fine. So square root of x, and when it says use the table of values, you have the control over what values you pick, right? You can pick easy numbers. Don't pick numbers that would make life miserable. So for example, for a function like that, I would pick numbers very easy. So I would pick 0, right? 0. When x is 0, square root of 0 is 0. 0 minus 1 is minus 1. Okay? If x equals 0, f of x equals negative 1. I'll pick another easy number, 1. If square root of 1, if x equals 1, square root of 1 is 1. 1 minus 1 is 0. I'll pick another really easy number, like 4. If x equals 4, square root of 4 is 2. 2 minus 1 is 1. I'll pick x equals 9, right? Really easy number for a square root. So a square root of 9, so if I pick x equals 9, then the square root of 9 is 3, right? Square root of 9 is 3. 3 minus 1 is 2. So I think that's enough values for us to graph this. So let's plot it. 0 comma negative 1 is here. 1 comma 0 is here. 4 comma 1 is here. 9 comma 2, it is here. You can already see the curve, right? It's not a straight line. It's a curve. It should be because we have a square root here. So let me draw it like as best as I can, like that. Okay? It's a curve like that. This one, once again, we pick easy numbers. So x and f of x. This is what the table of values will look like. I'm going to pick negative 2, negative 1, 0, 1, and 2. That should give us enough points to graph this. Minus 2 squared is 4. 4 plus 1, 5. Minus 1 squared is positive 1. Plus 1, 2. 0 squared is 0, plus 1 is 1. 1 squared is 1 plus 1, again 2. 2 squared is 4 plus 1 is 5, right? Let me do a couple of these. I mean, show how we plug them. So for, so function at negative 2 will be negative 2 squared plus 1. Negative 2 squared is positive 4 plus 1, because negative is also being squared, right? So equals 5. So we have negative 2 comma 5. That's what you see here. Let me do another one at negative 1. So the function at negative 1 equals negative 1 squared plus 1. Negative 1 squared is positive 1 plus 1. It's equal to 2. So we end up with negative 1 comma 2. Okay? So these values, these two values, are what you see here and here. And the rest you can do the same. So let's plot these points. Negative 2 comma 5 is here. Negative 1 comma 2 is here. 0 comma 1 is here. 1 comma 2 is here. 2 comma 5 is here. So you can clearly see a pattern emerging, right? So let's try to connect these dots with a straight, with a curve like this, smooth curve like that, Okay, so that vertex we will talk about later, I assume, in this course, and that is 0, 1. It's the lowest point of this quadratic function. Okay, so here we've reached the graphs of some typical functions. These are very important because any complicated graph can be broken up into parts of it that have one or two of these looks. What do I mean by that? Let me show you on a graph here. And I will use one of my thicker markers to draw that. Suppose, and that's the reason why we focus on these graphs, because people ask me, well, why these graphs? Because they keep coming up in this class, they keep coming up in Math 126 and other classes. And so why these particular ones? Here's why. Suppose we have a rather complicated graph. Let's say something like that. Right? Something like that. Now, to analyze this, you can analyze it as a whole. If you write a complicated program with a computer, you can analyze this kind of data as a whole. Or if you're interested, it's also possible to focus on pieces of it. If that piece interests you, then you focus on that piece for whatever reason. And that piece is more or less a straight line. So it's important for us to know the properties of a straight line, which they have constant slope. The constant slope can be positive or negative, and so on. If you're interested in analyzing this piece, that's a quadratic equation. See, that's a quadratic equation. This piece is a straight line. And that's I don't know if you've seen exponential functions before Math 124, I mean. If you have seen, that's an exponential function from here to here. Let me use another color like blue. So here, from here to here, that's an exponential behavior, this curve. So you have exponential function behavior. You have, so this would be exponential function. This would be a straight line. This would be quadratic function. And so on. So that's why, and even this, look at this curve, look at that, right? That pattern that goes like that. That pattern, that's a cubic function. Minus x squared, minus x cubed would be that pattern. From here to here would be almost a cubic pattern here. Okay, so that cubic function behavior. So that's why we focus so much on these functions, because you can break up data into patterns that exhibit these kinds of functions. Straight line function, cubic function, exponential function, quadratic function. Okay, that's why. That's why you have these. Quadratic with the bottom flattened. Why? Because this power, notice for the regular quadratic equation, x squared, you have a more pointed vertex. But as you increase this quadratic power by higher even powers, like x to the 4, x to the 6, x to the 8, and so on, this bottom gets flattened out. The same thing is true with the cubic function. See, for the regular function, cubic function, you have that pattern. And the one that I showed you, this one, it's going the other way. So this one would be y equals minus x cubed. But of course, it's going to be off-centered. So this pattern is associated with this kind of function, with a minus in front. But of course, it's not. This would be the actual graph. This one is off the origin. So it'll be a little bit different. Okay, but I mean, these distinctions you should be aware of, that when you have an odd power, cubic function, that if you increase the power by two higher odd powers, the intersection here, the inflection point is not something we look at in this class, but of course in Calculus 1, for those of you who will be taking that class, you will look at inflection, which is the point where you change from say, a concave down pattern to a concave up pattern. But of course, these are things you hear in Calculus 1. But, okay, so notice this junction and this inflection point here. For this graph, it's flatter. It's more flat. So is for this one. So compare the power here, the power of x to the 5, with x cubed, right? This is a higher odd power, so it's going to flatten that junction. And this is a higher even power, so it's going to flatten that bottom like that. I mean, we can switch back to the computer and look at this on the computer as well. I think it would be a good idea we did that. As I switch to the computer, you're going to see a glitch on the screen. Please ignore that. Everything is fine. Okay, but that happens when you switch from dock camera to computer. But everything should be fine. So, let me put this away, all this paper. Okay, so we want to graph the regular x squared function, right, which is that, like that. Now, see how that graph changes at the bottom. As I raise that power to higher even powers, y equals x to 4th power. See, did you see how the bottom flattens out? That's the effect. Let me change that power to 6, to even higher. Look at that. It's flattening, right? Doesn't it? So let me increase that to 8. Look at that. And if I go up to 10, wow. Compare that with the green one. So as you increase the powers to higher even powers, the effect is it'll flatten that bottom of the curve. So let's do the same thing with the cubic function, right? So I'm going to get rid of this. I'm going to make this cubic function. like that. And I'm going to make this a higher, so that's the green curve that you see is the original cubic function. Now let's increase that power to higher odd powers, not even, odd. See that? It flattened out, didn't it? So let me increase it to 7. Look at that. Compare the purple one with the green one. Look how flat it gets at that juncture, at that inflection point, as we increase the powers to higher odd powers. So 9, look at that. It looks like a chair now, right? And then 11, look at that. Really flat, doesn't it? Doesn't it look like really flat there? Okay, so I just wanted you to see how changing power would affect the behavior of the function. Okay, so we're going to go back to the dock camera. All right, so given these functions, we want to know how to find the domain and range of a function. So domain of a function is in all the possible values. So the domain of a function, those are any possible value that the independent variable okay, so this is starting by saying, it says to determine the domain, find any possible value that the independent variable, that is x, right? X or anything that, like t, like h, anything that can be x, that the independent variable cannot accept, exclude, this is the thing, exclude those values that the x value cannot accept. Find those values that x cannot accept, exclude those values, and everything else that is remaining is the domain of the function. Okay? So the domain of a function cannot include any values that might make the denominator of a fraction equal to 0. Very, very important. Okay? If you have a rational function, like the one we had, remember the one that for which -3 plus 3 made the denominator equal to 0? So in that case, we ended up saying that the function value at -3 does not exist, because we would end up dividing -7 or -7 by 0, which is undefined, right? So to find the domain, you find what values x cannot accept and exclude those, and then you have the domain of the function. So the fractions, so the first note has to do with fractions. So when you have fractions, this applies to fractions. This note, the domain of a function cannot include any value that might make the inside of a square root negative. Very important again, right? If a number, notice that the cubic root is okay. If you have this, let me bring this scratch paper back to make a point here, if I can find my scratch paper. See, if you have an even root, like square root of -4, this is a complex number. We're not dealing with complex numbers here, in this section at least. So if you have this, then there is no solution. So you want, for that reason, you want the inside of a square root to always be something greater than or equal to 0. Or if you have a square root of x minus 2, then x minus 2 should always be greater than or equal to 0. Something positive, because we don't want to deal with complex numbers unless the topic that we're dealing with specifically asks us to accept and work with complex numbers. But until then, we don't care about complex numbers. Okay? So wherever you have a square root, you must make sure that the inside of that square root is greater than or equal to 0. If you have an odd root, fifth root of x or fifth root of x minus 2, that condition no longer exists. You do not have to make sure that the inside of a radical expression is greater than or equal to 0. No. The domain of this function, well, the domain of that function was bracket 0 infinity, right? But that was for the square root of x. For a square root of x, that's the domain, because we don't want complex numbers. But for odd roots, like third root, fifth root of this, what do you think the domain is? The domain of functions like with odd root, 3, fifth root, seventh root, ninth root, the domain for all of these is negative infinity to infinity, because you can have a negative number under an odd root and end up with a real number that is not complex. So the fact that we talk about square root, a square root is one of those functions that is very commonplace in analyzing other graphs. It'll keep coming up again and again. But under a square root, because it's an even root means the fourth root is an even root, the square root is an even root, the sixth root is an even root. All of these values are even roots. So the sixth root of x is an even root. The eighth root of say x minus 5, that's an even root. Whenever you have an even, and a square root is also an even root, right? Every time you have an even root, you cannot have inside be a negative number. So you need to find numbers that make the inside of a square root negative and exclude them from the domain. Okay? So this one applies to square root functions. And of course, many times you'll see these two things mixed, right? Fractions and square root functions are mixed. How is that? Things like that. Things like, here are examples of that. If you have square root of x minus 2 divided by x plus 5, that's a square root mixed with a fraction. So you must make sure that that is never negative. So here x minus 2 is always either equal to 0 or positive, something greater than 0, which means x should be greater than or equal to 2 from the numerator. From the denominator, you must make sure that this is never 0. So x plus 5 should never be equal to 0, which means x can never be equal to negative 5. Right? And then the final domain of this expression is the domain that satisfies both those conditions. And the only way you can satisfy both of these conditions is by saying that one, right? 2 comma infinity would be the domain of that fraction, because it not only satisfies that condition, it also satisfies this condition, which x can never be negative 5. Okay? Okay, finding the range of the function. So to find the range of a function, we look at the dependent variable values, and we make note of what they cannot be. Whatever the dependent variable, or the y, f of x, or y values. That's what we're referring to when we talk about dependent variable. That's what we're referring to. When we talked about the independent variable, that's what we usually look at. But please keep in mind, the independent variable and the dependent variable can be renamed. So f of x could be g of x, or h of x, or d of x. It could be renamed. So what's important, when you look at a function, in your mind, establish which variable represents the independent variable and which variable represents the dependent variable. Okay, that's how you keep track. And then so for range, it's any values that are acceptable y values. So anything that is not acceptable in y, we find what those are and exclude them from the range. So before we look at the domain and range, the domain and range sometimes come in more than one piece, right? If the domain is one piece, fine. But if it comes into two pieces, then we need something to say, something in mathematical, among the mathematical symbols. We need a mathematical symbol that says this and that, this and this or that, this or that or both. We need a symbol to do that, okay? And this notation U and pronounced union, it fulfills that function, that it allows us to, when the domain has more than one piece, to mathematically say that this piece or that piece or both pieces. That's the symbol for that, the union symbol. Okay, you'll see this used again and again. Okay, so we have plenty of graphs for us to work with. I'm asking you to please download this blank worksheet off of Canvas. Then, on a piece of scratch paper, write down the domain and range for each of these cases before you see me work through them in the video. Okay, please do that. All right, I'm counting on you having done that, and now you have your own domain and range in front of you and are ready to look at what I write down. So, for domain, we need to look at the x-axis. We need to force our eyes, when looking at a graph, to look at the x-axis and exclude any restrictions on the x-axis or along the x-axis. Do you see any restrictions along the x-axis? Looking at the behavior of this line. Sorry, I was off the screen there. Sorry about that. So look at the behavior of this line. Do you see any restrictions along this graph that is related to the x? Is there any x value that this points on this line cannot take? Is there any x value? No. So what would the domain be? It would be minus infinity to infinity. All x values are acceptable. So the domain is negative infinity to infinity. The infinity side always gets the parentheses. The parenthesis means that the value next to it must be excluded. Right? That's what it means. Now, infinity is naturally excluded because we can, by definition, we can never attain infinity. If we could, we wouldn't call it infinity. It wouldn't be infinity. Infinity, by definition, means that we cannot attain it. We cannot get to it. Okay? So, when you look at the range, look at the behavior, when you're determining the range, look at the behavior of the graph with respect to the y-axis. Okay? With respect to the y-axis. Is there any y value that this line or this graph cannot attain? No. It can attain all y values. Therefore, the range is negative infinity to infinity. Okay? Look at this graph. Again, I'm assuming you've already have your answers written down. Look at this graph. The behavior of this line with respect to the x-axis, because we're working on the domain, right? So steer away or look away from the y-axis. We're focusing on the x-axis because we want to write down the domain. With respect to the x-axis, is there any value that this line, the points on this line cannot attain? Yes, there is one value, right? The value of x that this line cannot attain because of this hollow circle is x equals 1. X equals 1, this graph cannot attain. So what can attain? It can attain everything after it, everything before it, but not 1. So how do we reflect that? We say negative infinity, comma, 1, parenthesis, to make sure to exclude 1, and then the other piece, that piece. So union. This is why we needed to remind ourselves about what this symbol does. Union 1, comma, infinity. And we always write these intervals such that the smaller interval or smaller values are first and then the higher values. Okay? All right, so the range. The range, we need to focus our attention on the behavior of this line with respect to the y-axis. Right? So with respect to the x-axis, we already did that. Like that. And it couldn't attain the 1, but it could attain everything else. With respect to the y, then it attains everything here, it attains everything here, 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 and here. But wait a minute. There is some y value there that this function or this graph cannot attain. What y value is that? It is 0. This function cannot attain 0. Looking at the graph, we can tell that. After that, after y equals 0, it can attain all the other y values, right? So we say negative infinity, comma, 0, union 0, comma, infinity, parentheses. Parentheses everywhere because 1 and 1 are excluded, 0 is excluded, and infinity always gets the parentheses. Okay? So far, between these two examples we didn't have a bracket. We didn't have to use a bracket, right? But we'll get to bracket as well. Okay, so here we have a curve, the domain. Look at the behavior of this graph with respect to the x-axis. Is there any restriction? Notice the arrows. So if I could draw this, it would go off this campus, right? Because on both sides, these arms, this curve will continue on both sides. With respect to the x-axis, there is no restriction. If you say, wait a minute, there is a restriction, you got to show it. Where is it? Is there any x value that this graph cannot attain? No. It can attain all x values. So the domain would be negative infinity to infinity. The range. Is there any value, looking at this behavior, is there any y value that this graph cannot attain? Yes, because on the bottom side, it's coming up from negative infinity, right? But at some point here, up here, it cannot go beyond a certain y value. It just simply curves back down. So there is a maximum point beyond which this graph cannot go along the y-axis. What is that value of y? Well, if you look at this point, it says 1, 2. So the maximum point y value that this graph can attain is positive 2. Does it go through 2? Yes. Y equals 2? Yes. but then it curves back down on both sides. So the range is, it comes up from negative infinity, right? Negative infinity, comma, to bracket. Okay, I hope that's clear. Here, we have a graph that comes down from positive infinity and then hits a floor type of a point and then curves back up again. So with respect to the domain, is there any x value that this function cannot take? No, it can take all values. If you imagine these arms continuing in both directions, then it'll cover all x values all the way to infinity. It'll continue towards infinity. So there's no restriction on domain. So we write down the domain as negative infinity, comma, infinity. How about the range? Clearly, there is a limitation on the range, right? Because range has to do with the behavior of the function along the y-axis. So if it's coming down from positive infinity, there's a minimum limit it will hit, and then it'll curve back up again. What is that y value that it can attain? It is, if you look at the vertex, coordinates of the vertex here, it's -4. Y equals -4 is the lowest y value this graph can attain. So we say bracket -4, comma, positive infinity, because after y equals -4, this graph keeps growing towards positive infinity. Okay. This one, I'm hoping you've written down your solutions for these as well. So look at the domain. Is there any restriction on x values this function can take? No. If you continue these lines and look at the behavior along the x-axis, this function can accept all values along the x-axis. So the domain is -infinity to infinity. How about the range? Is there any value along the y-axis that this function cannot attain? No. It can attain all the y values along all the y values, right? So the range is also -infinity to infinity. All right. How about this one? Clearly, this graph has two pieces, right? So we must use that symbol we learned earlier a few minutes ago, the union symbol, to write down both pieces of this graph. So the domain is, look at each piece to figure out the domain for the whole thing. Look at each piece separately. So look at the behavior of this piece with respect to the x-axis, right? That's for the domain. So with respect to the x-axis, this function is coming from -infinity, and it approaches what x value as it curves down. As it curves down like this, it approaches x equals 0. So it cannot accept x equals 0. So for this piece, we have -infinity, comma, 0 parenthesis. And of course, the function is right here, 1 over x, right? 1 over x, x cannot be 0 because it would be, that whole function falls apart. It becomes undefined, right? So this is that piece. And again, force your eyes to look at the behavior of each piece with respect to the relative axis. So in this case, because we're working on the domain, we're going to look at the behavior of these two pieces with respect to the x-axis, not with respect to the y. At this point, we're not concerned about y. We're just concerned about what does this graph do with respect to the x-axis. Okay, so that's what that piece does. It comes from -infinity along the x-axis, and it approaches 0 along the x-axis. As it drops down, it approaches x equals 0. But it can never be 0, because 0 would make this denominator 0, and it would make the function undefined. Okay, so union, because we have a second piece, right? So what does this piece do with respect to the x-axis? Well, with respect to the x-axis, it starts again after 0. Right after 0, it starts again, and it approaches what x value? Infinity. It goes off the chart, off the page, off campus, so 0, infinity. Okay, how about the range? So let's look at the behavior of this graph, both pieces that is, with respect to the y-axis. This piece, it comes up from negative infinity with respect to the y-axis, right? Not x, y. It comes up with respect from negative infinity and it approaches some y value as it curves. When it curves, what y value is it approaching? Y equals 0. So negative infinity to 0 union the second piece. What does it do with respect to the y-axis? It is starting out right after y equals 0. It cannot be equal to 0. Right after y equals 0, it looks like it's starting and then it's going up to positive infinity with respect to the y-axis. So 0, infinity. So the domain and range look like the same for this interesting function, 1 over x. Okay, I hope this is making sense. For these two graphs, again, please write down the solution of your own and then come back to the video to see my solution. Okay, so the graph on the left, that one, has 3 pieces. So we're going to have to use that symbol union, right? We're going to do that. So we're going to look at, I'm assuming you've already written down your solution and you're back and you want to know if this solution agrees with yours. So the behavior of this piece with respect to the x-axis is that such that it approaches from negative infinity along the x-axis and it approaches some x value. What is that x value? Well, if you carefully look at the graph, that dashed line is going through x equals -1, and it's a vertical asymptote. Okay, so this piece is coming from negative infinity and is approaching but not passing through x equals -1. So let's write that down. Minus infinity, comma, -1, parenthesis. Parenthesis to indicate that the graph line does not pass through x equals -1. Then what happens? Well, this bottom piece happens. This bottom piece, what does it do with respect to the x-axis? Never mind what it does with respect to the y-axis. With respect to the x-axis, it goes from something higher than x equals -1 to something less than +1. Right? So let's write that down. Union, parenthesis, -1, comma, +1, close parenthesis. Parenthesis means that x equals -1 and x equals +1 are excluded from the domain according to this piece. Okay? The function that generates this graph cannot go through x equals -1 and x equals 1. And being the vertical asymptotes, that means that this would be 1 and -1 would make the denominator equal to 0. Okay, so the third piece, we need to put a union here again. Let's look at the behavior of the third piece with respect to the x-axis. With respect to the x-axis, this line, it's coming from somewhere a little bit higher than x equals 1, right? Never mind the y-axis. Look at the behavior of this line with respect to the x-axis. With respect to the x-axis, it's coming from something above 1, and it approaches to infinity as it curves this way. So union, parenthesis 1, infinity. Okay? Then the range. The range is looking at the behavior of all these three pieces with respect to the y-axis. So this time, never mind the x-axis. Just force your eyes to look at the behavior of each piece with respect to the y-axis. Okay, for this piece, the behavior is that it comes up from negative infinity with respect to the y-axis, and it goes through 0, right? It does go through 0, y equals 0. So negative infinity, comma 0, bracket. Okay, the curve does go through y equals 0. So 0 bracket, meaning 0 is part of the range. It's acceptable. Then it stops, right? It stops, and then again, the pieces pick back up again right after some y value. What is that y value? When you know that this is y equals 0 and that's y equals 2, so halfway in between that is y equals 1. Okay? So union, both pieces, not just one, both of these pieces start right above y equals 1 and continue to y equals infinity. So you say union, parenthesis 1, comma, infinity, parenthesis. Okay? That covers both pieces because their behavior is identical with respect to the y-axis. Okay. So now, this one, we have another graph with two pieces. We have to be careful where this curve stops and where it begins. So domain means we need to focus on the behavior of these two pieces with respect to the x-axis. So force your eyes to look at that behavior with respect to the x-axis, not the y-axis for domain. So this piece, with respect to the x-axis, it's approaching from negative infinity, and it's curving towards some x value. What is that x value? If you look carefully on the graph, that is x equals negative 2. That dashed line, as a matter of fact, it's right here. X equals negative 2. So you say negative infinity, parenthesis, negative infinity, comma, negative 2. Bracket or parenthesis? Which one? If you said parenthesis, wonderful, right? Because the graph does not touch that line. So it cannot attain x equals negative 2. And looking at the function in this corner, it's clear why, right? You plug in negative 2 in the denominator, it'll make the whole function undefined. So that's why. That's why we have this vertical asymptote. Okay, vertical asymptotes cannot be crossed. Horizontal asymptotes can be crossed. And, okay, so then we have the other piece, so union. What is this piece doing with respect to the x-axis? Well, it's this on this side, it begins right after x equals negative 2, right? Right after x equals negative 2, look what it's doing. It's starting. So, parenthesis, negative 2, comma, where is it going? It's going towards positive infinity along the x-axis. So, positive infinity, parenthesis. Okay? How about range? Well, you look at the behavior of these two pieces with respect to the y-axis. So look at this piece. With respect to the y-axis, what is it doing? It's coming up from negative infinity, which y, it's curving. So it's approaching some y value that it doesn't seem to like to cross. It would be this horizontal asymptote, right? The way it's approaching it, it looks like it'll never cross it. Even though horizontal asymptotes can be crossed, looking at the graph, we cannot assume that. We just say it's not going to cross the y equals 1 value, right? That dashed horizontal line is y equals 1. So it's approaching, with respect to the y-axis, it's approaching from negative infinity to 1, comma 1, bracket or parenthesis? parenthesis, right, because it's not going to cross y equals 1. Union, what happens after that? Well, the second piece starts. The second piece starts right above y equals 1, right after it, and it goes toward positive infinity, right? Positive infinity with respect to the y-axis. So 1 comma positive infinity, close parenthesis. Okay. So this section in your book, it talks about the vertical line test, and I thought I mentioned some things about it as well. So let me bring this scratch paper. So a vertical line test quickly can tell us whether the graph we have is a graph of a function or not. Okay? If it is, the vertical line crosses a graph more than once, then the graph is not. Let me highlight these. If a vertical line crosses a graph more than once, then not a function. Okay? So the vertical line test means the vertical line that you draw must cross the graph of the function at only one point. It cannot be more than that. If it is, then the graph you have does not belong to a function, it's something else. There are plenty examples of mathematical objects and entities that are not a function. Well, what are some of the examples? I don't want to, so if you don't mind, I'm just going to use this scratch paper to explain it. So you have, well, let's do this. So first of all, let's look at, so we're talking about just this. What is the vertical line test, right? So suppose we draw a graph like that, and we ask, is this a function or not? Well, graphically, you can run a test. You drop a vertical line, and it'll intersect the graph at only one point, anywhere. So this is a function. Okay, let me move that away for now. Okay. What about this? What if we have the graph that looks like this? Is this a function? Well, according to the vertical line test, if you drop a vertical line, it'll intersect the graph at only one point, at anywhere along the graph. So yes, it is a function. Okay. Interesting things happen too. For example, this is the graph of, this is a graph of, or a graph of y equals x squared. Right? That's the graph of it. Interesting thing happens if you do this. And let me keep this on the screen too. How about, oops, sorry, my y-axis didn't go as straight as I was hoping. But here's the point I'm trying to make. What about this function? Or what about this graph? Does this represent a function? Well, if you drop a vertical line, it'll intersect it at 2 points. So no, this is not a function. Interesting, right? This is a function. That's not a function. Not a function. Let me move this up. Not a function. So the interesting thing that I'm saying it happens is that that function has that graph. The function that generates this graph is x squared equals y. I meant y squared equals x. Let me correct that. So y equals x squared is that. y equals x squared is that y squared equals x has this graph. So that was a function. This is not a function. Right? It goes back to this thing that we talked about at the very beginning of this section. Remember that? When we talked about every value in the domain must correspond to exactly one value in the range, where here, if you have, in this, not there, but here, if you have, say, x equals 1, if x equals 1, then you can get that from y equals -1 and y equals 1. Right? So for x equals 1, there are two y values in the range. So one domain value corresponds to more than one value in the range, and that means we do not have a function. So this is very much connected to what we talked about at the very beginning of this section. Other interesting cases exist with respect to the absolute value function. So the absolute value function, y equals absolute value of x, has this graph. Right? Has that graph. Is this a function? Absolutely. You drop a vertical line here. It intersects the graph at one point, or anywhere along this. You can drop a vertical line, and it'll intersect the graph at one point. So this is a function. Right? But this function, if you switch these things around, so if you say x equals absolute value of y, then you end up with this graph. Is this a function? No, it's not a function anymore, right? When you have that. So not a function. Okay, by a simple swap of the variables like that, you get something that is not a function. What are other examples of mathematical entities that are not a function? There are lots of examples of them. Another example is something that we've talked about so far. Do you remember what that is? A circle, right? A circle, if you drop a vertical line, it'll intersect it at more than one point, so not a function. There are other entities like the ellipse. The ellipse is not a function, right? So the ellipse, we can draw a vertical ellipse, right? Drop a vertical line, it'll intersect it at 2 points. So again, not a function. Okay? So that's basically the vertical line test that we talk about here, and your book talks about it there. Okay? Okay, so next it says in each of the following cases, find the domain. All right? So look at this function. Is there any value that x cannot take? So when you talk about domain, always think about, is there any value that x cannot take? Because if there is such value, you need to exclude it, and everything else that remains is the domain of the function. So there is nothing that x cannot accept, right? X in this absolute value function can accept everything. So there is no restriction on x, therefore the domain is -infinity to infinity. If you say no, that's not correct, then you have to tell me what value of x you think that this function cannot accept. There's no x value that it cannot accept. It can accept all x values. There's no restriction on x. Therefore, the domain is negative infinity to infinity. How about the next function? Again, I hope if you haven't done this already, please pause the video and write down the domain. Think about it. Do what you need to do to write down the domain for each of these, and then come back to the video, unpause it, and watch what I've done. Okay? Please do that. Please do not skip that step. It's very important that you give yourself the opportunity to think and to write down your own solutions. Okay, so here, x cannot be 0, right? Because if x is 0, x is the denominator of this fraction. So x cannot be equal to 0. So we don't have to draw a graph, but if we do, maybe it'll help to see how this works. So here's the real number line. We have negative infinity to infinity. 0 is in the middle. And let me put a hollow circle right above 0, right? We know that x cannot be 0. So what can x be? Well, we have this side, and we have this piece, right? It can take all these values except 0. So for this piece, for this side, the domain starts from negative infinity, comma, 0. It comes all the way to 0. Parenthesis, because 0 is not acceptable. So parenthesis, union, this piece, which is 0, comma, positive infinity. Okay. Looking at this, is there any x value that this function cannot take? Can you think of any x value? Or can you not only think, but can you show mathematically if there is an x value for which this function cannot exist? No. This function, this is a quadratic function. It can accept all x values, right? So there is no restriction on x, so therefore the domain here is negative infinity to infinity. Okay, again, domain is the behavior of a graph with respect to the x-axis. As we go through these, it just occurred to me, let's graph these on the computer as well. So I'm going to go back and graph at least these few, just to get a visual feel for what's happening. Again, as I switch to the computer, you're going to see a glitch on the screen. Please ignore that. Okay, so we're back. Let me graph absolute value of 3x minus 2. See, that's the graph. And clearly, look at the behavior of this line or graph with respect to the x-axis. There is no restriction. All x values are possible. And the line, if I zoom out, let me zoom out, see the line continues forever. So all x values are acceptable. That means that domain is negative infinity to infinity, which is what we said. So let's look at that graph, 1 divided by, or y equals 1 divided by x to the 4th power. Right? As we expected, we can zoom into this. So the line gets very, very close to x equals 0, but it will never touch it. I mean, we can put a microscope there. See, as I zoom in on each arm, you can see the separation of x equals 0 value, or x equals 0, and the line of the graph, which is the red one. Right? See, well, let me, no, I'm going the wrong direction. Let me zoom out. Okay. Sorry about that. So here now we're on the right direction. So x equals 0 is right here in the center. Look at as we approach x equals 0, this line gets closer and closer to the y-axis. You see that? But it will never touch it, because at that point x equals 0 on the y-axis, x equals 0, and we know from the function that the function cannot attain that because it will be undefined for that x value. So look at how this line keeps getting closer and closer to x equals 0 value, which is the y-axis, but it will never touch it. Okay? So I wanted you to see this behavior of the graphs. Okay, like that. Like that. So that trough-like behavior, the way curves go up, that's where we have asymptotic behavior, because the function cannot attain x equals 0, right? This function here. Okay. Let's look at the quadratic function that we just looked at, which was 1 over 5 times x squared minus 5, right? So if I zoom out, see, look at the behavior of this graph with respect to the x-axis, which is the domain. Domain is what we're working on right now, right? So with respect to the x-axis, it can attain all possible x values. So therefore, the domain of the quadratic function is negative infinity to infinity. So let's go back to the dot camera. This was just gave us a visual sense of what we've been talking about in terms of these numbers. Okay, so this one, I hope you have your solution for this one. You already have your domain, and you're waiting for me to finish my work, which is great. So here we have a fraction. With fractions, we cannot have 0 in the denominator. So 2 minus x cannot be equal to 0. We know that. So let's find what value x cannot take. Solve this for x. We get x cannot be equal to 2. Therefore, the domain would be everything except 2. Everything except 2, right? We don't have to draw a graph, but I think it helps if we do. So we have negative infinity and infinity, 0 in the middle. We say that because 2 would make the denominator 0 and the function undefined, we cannot have x equals 2. So if this is 2, I'm going to put the hollow circle over it, meaning that the domain cannot take 2. What else then domain can take or accept? Well, it can take all these values, and it can take all these values. For these values on the left, we can write negative infinity to 2 parenthesis, because 2 is not acceptable, so parenthesis. Union, the other piece, 2 comma positive infinity. So the domain of this fraction or this rational function is that. And by the way, you will hear and see this a lot, so let me say it. This is called a rational function. Okay? So this last page 8, please make sure that you write down the domain for all of these before you see my solutions. And please, again, please do not skip that step. So I'm assuming you've already done that, which is great. Now you should have the domain for all these 5 functions. Okay, so here we do not want x or x plus 4 to be 0, right? So x plus 4 equals 0 or not equal to 0 makes no difference, but we're going to solve for x. X equals negative 4 is trouble, right? When x equals negative 4 is trouble because if we make the denominator 0 and the function undefined. So we need to exclude negative 4, right? We don't have to draw the graph, but maybe it helps if we do. So here's negative infinity to infinity. Where is negative 4? Negative 4 is somewhere here. Let me put a hollow circle on top of it, and this is negative 4. So what is the domain then if it cannot take negative 4? Well, it can take these values, and it can take these values. So let's write down the interval notation for each piece. For this piece, we have negative infinity to negative 4, parenthesis, right? Negative infinity to negative 4, parenthesis, because negative 4 is not acceptable. Union, that piece, which starts right after negative 4. Negative 4, again with parenthesis, means negative 4 is excluded, comma, infinity. And that is the domain for that function. Okay? This one. This is an interesting case because we need to, it's a rational function. That was a rational function. This is a rational function. Right? So let me make that clear. This is a rational function. And with all rational functions, we need to make sure that the denominator is never 0. But how can we know when the denominator is 0? Two ways. You can either factor it. You can either factor the denominator and set each factor equal to 0 and find those numbers that would make the denominator 0. Or you can apply the quadratic formula, because that's a quadratic equation. You can apply the quadratic formula, find what x values make that equation or that quadratic equation equal to 0, and then exclude them from the domain. I think these numbers are easy, so we should be able to graph this, which means we're going to save time because using the quadratic formula will take a little more time, right? So let's factor the denominator. We have f of x equals 1 over, if we factor, we get x minus 5 times x plus 1, right? These are easy numbers, so we can easily factor this out. X times x is x squared. X times 1 is x minus 5x. Minus 5x plus x, we get minus 4x. Minus 5 times 1 is minus 5. Okay? So if you FOIL this, you're going to get this back. Okay? So now since we factored the denominator, so the lesson you should take away from this particular example is that whenever you have an expression that is not in factored form in the denominator, you must factor it. Okay? Factor the expression in the denominator to see what makes the denominator equal to 0. So let's solve each one for 0 and see what values will make the denominator equal to 0, because we're going to need to exclude those values from the domain. So if x minus 5 equals 0, then x must be 5 must be excluded from the domain. Okay, so we found 1. If x plus 1 equals to 0, then x equals negative 1 must be excluded from the domain. So we don't have to draw a graph, but I think graph in many ways will make things clearer. So why not draw it? So we have negative infinity on this side, positive infinity, 0 is in the middle, somewhere there. And then we have to exclude 5 and negative 1 because those two values will make the denominator equal to 0, which we do not want, right? So negative 1 is here someplace. Let me put a hollow circle there, negative 1. And positive 5 would be 1, 2, 3, 4, 5. So let me put a hollow circle there, 5. So those two numbers should be excluded from the domain. Then what is included? Well, we have this piece, and this piece, and this piece, right? 3 pieces. Let's write down the domain, given these 3 pieces. The domain is, for this piece, from here to here, we get negative infinity, comma, negative 1, parenthesis, because negative 1 is not included. Union, negative 1 to 5, parentheses again, to ensure that 5 and negative 1 are not part of the domain. And of course, union, that last piece, which is 5, comma, infinity. And sorry for mixing things up here. I'm running out of room on my paper. So let me do that. That's the domain. And that was negative infinity over there. Okay? Is this clear? I hope this is clear. If not, please let me know with your questions. So here we have something really interesting. Because even though we have a root, we have a radical expression, but it's a cube root. It's an odd root. Okay? For an odd root, we are allowed to have negative and positive inside the radicals. Let me write that down. For odd roots, we are the inside of the radical expression can be negative or positive. It's the square root and all the other even roots that cause problem for us because they create complex numbers. And most of the times, we're not interested in complex numbers. So we need to be careful with the domains of even roots. This is an odd root. So anything is acceptable. It can be negative inside the radical. It can be negative. It can be positive, anything. So therefore, the domain, it has no restriction, and it is equal to negative infinity, comma, infinity. Okay? Now, compare this with that. H with G, right? The only different thing, they're identical in every way except the root, index of the root. Now we went from odd root to square root. That's a huge change. Even the look, most of the look stayed the same except the root changed from cube root to square root. Right? That subtle but important change means that the inside cannot be negative now because we have an even root. So, therefore, x plus 10, that inside can be 0 or can be something positive, but it cannot be negative. How do we guarantee that? Well, we set that whole inside into an inequality, and we solve the inequality. We say x plus 10 can be 0 or can be something greater than 0. That's an inequality. We need to solve that. So x is greater than or equal to negative 10. Perfect. So now we can write the domain using the interval notation. Domain is bracket or parentheses. What do you think? Let me put this negative 10, negative 10. What I'm asking is, do I put a, well, let me complete. So negative 10, comma, anything greater than negative 10, positive infinity, right? So for infinity side, we know it always gets the parenthesis. But what about the negative 10s on this side? Do I put a bracket or do I put a parenthesis? I would put a bracket. A bracket means that negative 10 is part of the domain, is part of the solution. Because if you plug in negative 10 plus 10, you end up with square root of 0. Square root of 0 is 0, right? We can test it. I mean, it's defined. It's just 0, but it's defined. So we can take square root of 0. What do we get? We get 0. So it is defined. So in this case, we have bracket negative 10, comma, infinity, which is that. Okay, so we set up an inequality to ensure, to solve for what makes the inside 0 or greater than 0. So those are all the x values equal to or greater than negative 10 that would make this inside either 0 or something positive. We got it, right? Here something interesting happens. We have a rational expression again, right? With rational expressions, as you know, the denominator cannot be 0. So let's factor the denominator, because right now it's really not apparent what would make the denominator 0. So let's factor the denominator. We have f of x, and that's an easy expression to factor, right? 8 minus x, factor which term? X. Factor out x. When you factor, factoring, again, it's the opposite of the distributive property. So how do you know you factored something properly or accurately? Simply distribute the x into the terms to see if you get that back. So x times x, x squared. X times minus 7, minus 7x. So we got it. This is the correct factorization. So now that you have the denominator figured out in factored form, it's really easy to see what makes it equal to 0. So if x equal to 0, f of x is undefined, right? So one of the x values we need to exclude is x equals 0. How about the other value? Well, the other value is if x minus 7 equals to 0, then x equals 7 must be excluded from the domain, right? So we have two values we need to exclude. One is x equals 7 and one is x equals 0. Both of those will make this expression, this function undefined. So let's write down the domain. Well, before that, let's graph this, right? So let me come up here and put the graph here. Okay, so x equals 0 should be excluded. So I'm going to put a hollow circle there. X equals 7, somewhere there, should be excluded, right? So what is included? This piece, all of these numbers are included. All of these numbers included. All of those numbers included. So let's write them up. Domain is equal to minus infinity to 0, parentheses or bracket? If you said parentheses, wonderful. Yes, 0 must be included. We just said that, right? 0 and 7 must be excluded. Union, this piece, parentheses 0, comma 7, parentheses or bracket? Parentheses. Union, that piece, parentheses 7, comma infinity. So there's the domain of that rational function. Like that. Okay, so we have come to the conclusion of another section here. Please maintain the course. Even if I forget to mention it in these videos, please solve all the problems before you watch the video. It doesn't matter how incorrect your solution may be. What's important that you're writing down your own thinking. That's critical in learning, especially this subject. So even if I forget to say it, please, you don't forget to do it, and then unpause the video to see my solutions. Okay? And thank you for persisting through this video. Until next time, have a nice day.